Alright, we're looking at optimization. Here's a real-life problem from section 4.6. This is problem number 9. And what we're looking at is somebody's planning on building a storage shed. And what the information we're given is that they know what volume they want it to be. So they know what size they want it to be. They want it to be 810 cubic feet. So that's one thing they know. Some other things you'll notice that they know is that it is a box shape. Okay, so that means everything is at right angles to every other edge, and so that gives us a rectangular shape that's been extruded into the third dimension. So we know it's rectangular by nature, a rectangular prism. And we're also told that the base of the storage shed is going to be square, which means that the length is equal to the width. So from what we know, we can draw this and say the floor has length, width, the walls have height. And from what we're told, because it is a square base, we can say that length equals to width. So instead of writing this as length, I'm just going to write this as width as well. So it's square, so its base is width by width. We're also given the prices of the different types of material. We're given the cost of the top material, or the roof material. By the way, it's just a flat roof, and that is $3 per square foot. We're also given the price of the wall material, which is $4.5 per square foot, and the floor material, which is $7 per square foot. And we're trying to minimize costs. So let's write that up here. Minimize cost. Alright, so what we can do here is we need to write a cost equation. And how we do that is we're going to start by realizing that all of the prices are based on square feet, and square feet has to do with area. So all of these walls and roofs and floors have area. So let's solve for the area of the floor. So the area of the floor can be written as width times width, right? That gives us the area of the floor. So we'll say that's width squared. And that's also the area of the roof, if you noticed, because it's a rectangular prism. So the area of the floor and roof are W squared. And there's one floor and one roof, so we've got 2W squared. Now the area of the walls, well, we're going to go and take a look. So the area of an individual wall would be width times height. But we have 4 walls, so the area of all the walls total is 4 width times height. And so now at this point we're going to go ahead and write a cost equation. This is going to be one of our master equations. So the cost, I'm going to indicate that with C, is going to equal the area of the floor times the cost of the floor material. So the area of the floor is W squared. The cost of the floor material is $7. $7 times the area of the floor. So with units, that would be $7 per square foot times the amount of square foot in the floor itself. Then we're going to add the wall material. The wall material is $4.5 per square foot, and we have 4 WH square feet. So 4 times 4.5 leaves us with 18 WH. So 18 times width times height will give us the cost of the wall material. And now we're going to add the roof material, which is $3 per square foot, times the area of the roof, which we decided was width squared. So this is kind of our master equation for minimizing cost. But you may notice here that there's 2 unknowns. There's 2 variables in here. There's width and height. And we can't quite solve for anything at this point with just that known. Luckily, we're given the volume. So we're given the volume of the box. It's 810 feet squared. And we know that volume is length times width times height. So if volume equals 810 cubic feet, then we know that our length, which is our width, times width, which is width squared, so width times height, W squared H is equal to 810. And so what this is essentially telling us is even though we have 2 variables, they're actually dependent on each other because of the fact that we know what the given volume is supposed to be. So we can solve for height in terms of width. And so let's divide w squared over here, and we'll solve that h equals 810 divided by width squared. And so now that we know that, we can plug that in for height in our cost equation, and that's going to simplify us down to a single variable. And to do that, I'm going to erase this nice drawing to make some space, and we'll write it up here. So cost is now equal to 7 times w squared plus 18w times h. And remember, h is equal to, using our volume, h is equal to 810 over w squared. 18 over w squared plus 3w squared plus 3w squared for the roof. Now we've got like terms of 3w squared and 7w squared, so we'll add those together to make 10w squared. And then we're going to cancel some things, right? Because this w will cancel with one of the w's in the denominator, and we'll be left with a w in the denominator. And above it, we'll be left with 18 times 810, which is 14,580. And so this is our cost formula in terms of w. So what we're going to want to do is we're going to want to minimize cost by choosing what that width is going to be. And to do that, we're going to take the derivative of c with respect to w. And of course, we can write this as ddw of 10w squared. Using linearity, we can take the derivative of this one separately. ddw, I'm going to write the w in the numerator as w to the minus 1. So now we're left with 14,580 w to the minus 1. Once again, need more room. Let's see here. So let's go ahead and take the derivative. This one is a nice power rule one. That just gives us 20w. This one's a little trickier. Due to the linearity, I can plot the 14,580 and just push that back into the derivative of w to the minus 1. So the derivative of w to the minus 1, we bring the minus 1 down, and we subtract 1 from the power. So that gives us minus w to the minus 2. Because we brought down the minus 1, we subtracted 1 from the power. And if we rewrite this, so our change in cost with respect to our width is now going to be equal to 20w plus 14,580 over, I'm going to put the w squared in the denominator. I'm sorry, minus, because remember this minus in here is going to be factored out. So 14,580 divided by w squared. And remember, we're looking for critical points, points where we're at a minima or a maxima. And so to do that, we're going to set our derivative equal to 0. And let me make some more room up here. These problems can be kind of long, but it's really the setup. It's the setup that's the hardest part. Once you know what you're doing, it's pretty much just algebra from there. So now we're trying to solve for this equation, which is 20w minus 14,580 over w squared is equal to 0. So the first thing we look at is we're going to go ahead and factor out a w for both terms. That's going to give me 20, because I pull out a w, minus 14,580 over w cubed. If you don't believe me, multiply it back in. W to the 20 is 20w. W to this would cancel one of the w's in the denominator, giving us w squared. Now, is 0 a valid option for this problem? It's not, because even though 0 might look like it's a solution, that would require us to divide by 0, and that does not exist. So we're just going to get rid of this w and ignore it by dividing it into 0. And then what we're left with is 20 minus 14,580 over w cubed equals 0. We'll subtract 20 over. subtract 20 over, times both sides by a minus sign, which is going to get rid of that. We're going to multiply w cubed on both sides, just like that. Then we're going to divide both sides by 20. And this number, 14,580, divided by 20 is 729, and that's equal to w cubed. Now I'm going to take the cubed root of both sides. The cubed root of 729 is a beautiful number. It is the number 9. And pretty much with a problem like this, if you come out with an even number, the odds of that are really slim if you didn't get the problem right. So whenever I see a nice integer like that, I'm usually pretty happy. So what this is telling us is that our base is 9 feet by 9 feet. Okay, so we know one of the things. We know that the width is 9 feet. Let me go ahead and fill in a unit there. So the width is 9 feet. Next question is going to be about the height. What's the height? Well, we know that volume is 810, right? And that volume is equal to length times width times height. Well, our length and our width are both the same length. They're 9 feet, so that's w squared. And then times the height. So w squared is 9 times 9. That's 81. So 810 equals 81h. We divide both sides by 81, and 810 divided 81 is 10. So we've now solved that h, the height, is 10 feet. That sounds like a pretty good storage shed. And of course, one more thing I think that's important before I move on is how did we know that this was a minimizing of the cost? And to do that, one, you can graph the function, right? If it's a minima, then you know that we're minimizing that cost function. But if you don't have a graphing calculator, then it's going to be important, because remember our derivative of c with respect to w, derivative of cost with respect to the width was equal to this, right? 20w minus 14,580 over w squared. And instead of setting it equal to 0, let's take the second derivative and look for concavity. If you're not sure what I mean by that, you may want to check out my video about graph sketching and concavity. So we're going to take the second derivative of cost with respect to width. And of course, 20w, the derivative of 20w is just 20 minus, let's write this out differently. We'll write it as d dw, and I'm going to pull out the constant because linearity. The width of width to the minus 2, bring that to the numerator, and change the sign on the power. So we bring down the negative 2, so we have negative 2w, and subtract 1 from the power, negative 3. And so now we can rewrite our second derivative of cost with respect to the width as equal to 20 minus 2, that's going to make this positive, right? Minus times a minus. 14,580 times 2 is going to be 29,160. And this is all over w cubed. Alright, so the next step is we're going to set this equal to what our value is. So we're testing when w equals 9 feet, are we concave up or concave down? Because if we're concave up, we're looking at a minima point. If we're concave down, we're looking at a maxima point. So we're going to plug in to this second derivative, w equals 9 feet. And so we get 20 plus 29,160 divided by w cubed, that's 9 to the 3, 729. And so 29,160 divided by 729 is 40, plus 20, we're getting a 60. So in other words, I could write this as c double prime. The second derivative of cost, we've plugged in the width is 9, and what we're getting out is we're getting out 60. 60 is a positive number, and therefore we know that we're looking at a positively increasing slope. So the rate of change of the slope is positive. That points towards concave up, and concave up means that the point we found is a minimizing point. So here's how we prove that we truly minimized the cost. As we take the second derivative, we plug in the value that we solved for. If we end up with a positive number, we have truly minimized it. If we end up with a negative number, we've actually maximized it. But because we only got one value out of the algebra, I kind of skipped this step intuitively, because I figure if they're asking about minima, and the one critical point I have is 9, I'm just going to assume that's a minima. But that's not always a valid assumption, so definitely double check with the double derivative. If you don't feel like taking the second derivative, then at least graph it on your calculator. Make sure that in the range of the graph, domain of the graph, that there is a minima at the point that we found, which is w equals 9. So I know this was a long video. Hopefully it was helpful. These problems can be hard to set up, but once you practice enough of them, the setting up will become easier and easier. So I hope this was helpful, and I'll see you next video.